To the problems solving session 9. So in this problem solving session, what we will do, we will go through some of the problems from the assignment 9 because you have to submit the assignment 9 by tomorrow. So I thought it will be a good idea to go through those questions as well as solution, and then you can revisit that problem set, and then you can solve some problems if you have not solved them yet. So first, what I will do, I will start with some of the properties of Z transform, because this is what this assignment is all about. So first, let's go through some of the properties of the Z transform that will be useful in order to solve the following problems. So here are some of the properties of the Z transforms that will be useful in order to solve this assignment. So first property is the multiplication property. So suppose you have some sequence un and you know the Z transform of that. So the Z transform of n times un is given by minus z times derivative of uz, which is the Z transform of the sequence small un. Okay, so this is the first property, which is called multiplication property, and it is quite useful in order to solve some of the problems. The second property is the change of scale property, or also known as damping rule. So suppose if you have some sequence un and the Z transform of that is given by uz, then you can calculate the Z transform of un by a power n, or an times un, uh, like this. So you can write Z transform of a minus n un is equal to u times az. Now function u, in function u replace z by a times z. And similarly, if you have if you want to find the Z transform of this type of sequence, which is a power n un, you simply replace z by a in the Z transform of un. Okay, so this is the second property, and this is also quite useful, and that we will see when we solve the problems from the problem set. The other thing is the initial value theorem. So initial value theorem says if you have some sequence un, small un, and you know the for Z transform of that, so this Z transform of un is given by uz, then you can calculate the following functions. Like you can calculate u naught. So u naught can be calculated by taking the limit on capital uz from z to infinity. Similarly, u1 you can calculate by using this equation, and similarly you can calculate all the functions in that to un. Okay, so this is the initial value theorem, and the last thing is the final value theorem. So here what it says if zun is equal to uz, so you have some sequence u small un, and the Z transform of that is given by uz, then the limit un with n approaches to infinity is same as limit z approaches to 1 z minus 1 uz, and this is also quite useful in solving some of the problems. So this was all the properties that we will be using in order to solve this problem set, and I hope all of these property you have already studied in class or your lectures. So this was just a small review of all the properties that I will be using in order to solve this problem set. So okay, after the review of the following properties, so let's start with the solving some of the problems. So all problems will be from the problem set only. So I will urge you to go back and solve the assignment set if you have not solved it yet. And here I will be giving you a type of hint, or I will be solving some of the problems, and then you can solve it by your own. Okay. So let's start with the problem set, problem number one. So problem number one is you have some sequence u small un, which is given by n sine n theta, and you need to find the Z transform of this. Okay. So how we can solve this problem. So this is a very straightforward problem, and let's see how to solve this. So first, if I just ask you like what is the z transform of sine and theta, right? So this is a very standard form or z transform of sine and theta, and it can be easily calculated. So the z transform of sine and theta is given by z sine theta upon z square minus 2z cos theta plus 1, right? With the modulus of z greater than 1 to say that the series is converging. So now the question is asking like you already know what is the z transform of sine and theta, and the question is asking like what will be the z transform of n times sine and theta. So if you revisit this property, this the multiplication property, you can see if you know the like the z transform of un sequence, and then you can easily calculate like what will be the z transform of n times un. So this can be just calculated by minus z d by dz of uz. So you basically take the derivative of first the sequence z transform of the sequence un, and then you simply multiply it by minus z. So let's use this property and solve the following problem. So here I can write again like whatever I showed you on the previous slide. I can write it as minus z by times d by z dz, and the z transform of sine and theta, where sine and theta is correspond to the sequence un, right? Now what you do, we already know like what is the z transform of sine and theta. So basically we rewrite this equation by replacing the z transform of sine and theta. So the z transform of sine and theta can be written by z sine theta upon z square minus 2z cos theta plus 1, right? So now you see in this equation, you need to take the derivative of whole function with respect to z, right? So you see theta is not a function of z. So what you can do in order to do the derivative of this, you can use quotient rule. So basically you first uh, uh, take the derivative of z by keeping this constant, and then you take the derivative of denominator by keeping z constant. So here I have done the same thing. So let's see. So minus z times sine theta, which is not a function of z, so it will come on both sides. And then first I am taking this function as it is, so z square minus 2z cos theta plus 1, and then I am taking the derivative of z. So dz over dz will be 1, so here it will be 1. Then minus times z sine theta, so here I am keeping this function as constant and I am taking the derivative of this. So the derivative of the denominator with respect to z will be 2z minus 2 cos theta, and then you have the square of the denominator. So this is what the quotient rule of the derivative says. So then I can just simply rewrite this equation like this, and this gives you the z transform of n times sine n theta. So you see like if you know the z transform of sequence sine n theta, then you can easily solve this problem by calculating the z transform of n times sine n theta by using the multiplicative property of the z transform. Okay, so this was the first question. Now let's move on to the second question. So the second question is, if you have some sequence un which is given by e power 5n times sine 3n, so you need to calculate the z transform of this. So again like you can see it's mostly like the previous problem, but here we use different property in order to solve that. So let's see how to do that. So again, like we already know like the what is the z transform of sine and theta, right? From the previous question, we know that z of sine and theta will be z sine theta upon z square minus 2z cos theta plus 1, right? Now the question is asking sine 3n, right? So what I do, I replace this theta by 3. So if I calculate the z transform of sine 3n by replacing theta by 3, I get z sine 3 upon z square minus 2z cos 3 plus 1, right? Now you have the z transform of sine 3n, and you need to calculate like what is the z transform of e power 5n times sine 3n. So now again if we revisit the property, second property, which is this, like if you know like what is the z transform of sequence un, then you can directly calculate the z transform of a power n un by replacing just z by z by a, right? So here in this question, if I take a is equal to e power 5, right? If I take a is equal to e power 5, then this questions completely satisfy the property, that property I can use in order to solve this problem. So as I told you, now you have the z transform of sine 3n, and you need to find out what is the z transform of a power n e power 5n times sine 3n. So we use this property and we replace, as I told you, you replace z by a. So if you replace z by e power 5, because here a is e power 5, so you again rewrite this so in this expression you just replace z by e over 5. So if I do that, I get z sine 3 upon e power 5. Similarly, in denominator I have a square, so it will be z over e power 5 square minus 2 times z over e power 5 cos 3 plus 1. And now if you just simplify this uh, equation, you can get the z transform of e power 5n times sine 3n. So again, by using the second property of the z transform, you can easily solve this problem. And again, I urge you, it's very easy to solve problems when you know the standard z transform, the z transform of some standard function. Like here, in both the question we use the z transform of sine and theta. So if you know this prior to solving the question, then it's very easy to solve such problems. Okay, so this was all about the second question, and I hope it's clear to you. So let's move on to the third question. So the third question is, if if you have a sequence and you are given the, if z of un is equal to uz, and you are given the capital uz of that, like 3z square minus 5z plus 8 upon z minus 2 power 4, with the mod of z more than 2, greater than 2, then you need to calculate like what are the u1 and u3 for this given capital uz. So now again, like if you see this property, which is the initial value theorem, it clearly says like if you know like what is uz you know capital uz, which is the z transform of some sequence un, then you can simply use this formula to calculate u naught, u1 or u2 or u3. So here again doing that, the question is asking like what are the values of u1 and u3. So in this question, the question is demanding to use the initial value theorem, right? So let's see that how to do that. So first of all, if you see the question is asking u1 and u3, and if I go back to the property, in order to calculate u1, you need to first calculate like what is u0, and similarly if you want to calculate u3, you need to know like what are the u1 and u2 of that, right? So we need to calculate both like u0, u1, u2 in order to calculate u3. So let's try to solve the problem. So first, as I told you, the u naught value of u naught is given by limit z approaches to infinity uz. So limit z approaches to infinity, uz is given by 3z square minus 5z plus 8 upon z minus 2 power 4, right? So here you see denominator has power of z has power of 4, and if I take limit z approaches to infinity, this function will approaches to 0. So u naught you know now, so u naught is given by 0. So u naught can be easily calculated by taking the limit on uz with z approaching to infinity, and u naught you can calculate directly, which is 0. So now you know the value of u naught, but now question is saying you need to calculate u1 first. So let's calculate u1. So what will be u1? u1 is limit z approaches to infinity z times uz minus u0, right? So u0 now you already know, which is 0. So you can rewrite this equation. You can write it as z times 3z square minus 5z plus 8 upon z minus 2 power 4 minus 0, right? And again, the denominator has more power of z compared to the numerator. So when you take the limit of z approaching to infinity, this will go again go to 0. So again you get the value of u1 is equal to 0. So using initial value theorem, you get both the value of u0 as well as u1 is equal to 0. So now question is saying calculate u3. But in order to calculate u3, first you need to know what is the value of u2. So the value of u2 can be calculated while limit z approaches to infinity, z square uz minus u0 minus u1 by z. So this formula is coming from the initial value theorem. So what you do, you just put the values of u0 and u1 in this equation. So if I do that, I get z square times uz function, which is as it is, minus 0 because both u0 and u1 are 0, right? So now if I again try to take the limit on this, I see now the both numerator and denominator both have z power 4, right? Because here if you multiply z square in the numerator, the highest power of z will be z power 4, and similarly in the denominator you have z power 4. So this is basically the infinity by infinity form. So the limit on this can be calculated by using the L'Hopital rule. So here if you use the L'Hopital rule, you will get limit z approaches to infinity, u2 will be 3 because the coefficient of z power 4 is 3, and in the denominator the coefficient of z power 4 is 1. So basically you get the value of u2 is equal to 3. So now you know all the values, like you know u0, you know u1, and you know u2. Now you need to calculate like what is the value of u3. So let's see how to do that. So the value of u3 will be limit z approaches to infinity, z cube times uz minus u0 minus u1 by z minus u2 by z square. Again this is coming from the initial value theorem. So let's try to simplify this. So I have z cube, and then I rewrite the function uz as it is, and then I have minus 3 by z square because the value of u2 is 3 and the value of u0 and u1 are 0. So I will get this equation. Now if I try to resolve this, I will get z cube times uz minus 3 by z square. So I am again rewriting this equation like this. And now what you can do, you can take the LCM, like if you take the LCM here and you rewrite this equation, so the LCM here will be z square times z minus 2 power 4, and the z square will be cancelled by z cube, so you will left with 1z, and in the numerator you will get the following function, right? So you get 3z4 minus 5z cube plus 8z square minus 3 times z minus 2 power 4, right? So I can again rewrite this equation by multiplying z inside. So if I do that, I will get z times this whole function, right? Where I have simplified the z minus 2 power 4 function in this. Now you see the 3z power 4 in the numerator. So there are two values, one with the positive sign, another with the negative sign. So you basically cancel both 3z power 4 in the numerator by simplifying this equation. Now if I again rewrite this equation, I will get z times 19z cube minus 64z square plus 96z minus 48, right? Again rewriting this equation, right? So now you can easily take the limit on this. So if you see again in the numerator you have z power 4, and in the denominator also you have the highest power z power 4. So basically when you take the limit z approaches to infinity, the limit will converge to the coefficient of z power 4. So the coefficient of z power 4 here is 19. So the value of u3 will be 19. So here if I go to the answer, so the u1 value of u1 is 0 and the value of u3 is given by 19. Okay, so you see this problem, like whenever the question is asking to calculate some of the functions like u1 u3 of the sequence, then you need to use the like initial value theorem in order to solve that problem. So okay, so I hope this problem is again clear. So let's move on to the next question. So the next question is, you are given some uz, capital uz, which is the z transform of some sequence, and this is given by 1 upon z minus 2 z minus 3, and you are given like the modulus of z lies between 2 and 3. So and now you need to calculate like what is the inverse z transform of this. So let's see how to solve this problem. So what you can do first, you can rewrite this equation, like I can rewrite this capital uz like this, right? It's very easy to write in this fashion. If you add plus minus 1 on top, then you can rewrite this like this. Now you see the from the this limit. So limit is saying modulus of z is more than 2, but it is less than 3, right? So now I need to see like this is the sum of some like infinite geometrical progression series, right? So if I take 3 outside, so let's just see the first term for time being. So if I take minus 1 by 3 outside, right, from here, so what I will left with, I will left with 1 upon 1 minus um, z by 3, right? I will left with this 1 upon 1 minus z by 3 if I take minus 1 by 3 outside. And this is saying limit that modulus of z is less than 3. So basically from that I can write the series summation of this, right? So if you know, if the infinite sum of some geometrical progression is given by this, then I can write the simply the geometric progression sequence. So here I have taken the minus 1 by 3 outside, and my common ratio will be z by 3, right? And from the limit it is clear that modulus of z by 3 is less than 1, so this series will always converge. So if I rewrite this, I will get n0 to infinity 1 by 3n times z power n, which is nothing but the series summation of this infinite uh, uh, sequence what is given. Okay, now if you see the second part, right, now you can think like again here I will take 2 outside, right? So if I take 2 outside, minus 1 by 2 outside, what I will left with, I will left with 1 upon 1 minus z by 2, right? But if you see now, modulus of z is always greater than 2, so this series is not converging, right? So what you need to do, you need to take z outside here. So if you take z outside here, what you will get, you will get 1 upon if you take 1 by z outside, right? So what you will get, 1 upon 1 minus 2 by z, right? So here the common ratio is 2 by z, because 2 by z is less than 1 here from the given equality. Therefore, this series will converge. So now here the common ratio of the geometrical series is 2 by z. And if I use that thing, then for this function also I can write the infinite geometrical progression series. So by doing that, I can rewrite both of these series like this, right? Now again rewriting this, I am rewriting this as minus 1 by 3 summation n 0 to infinity 1 by 3n times z power n. And here I am writing, so here you see power of z is given by minus n minus 1. But if you recall like what is the z transform, then the power of z should be minus n, right? So what you do here, you replace n by n plus 1, right? So if you n minus 1, so if you do that, if you replace n by n minus 1, what you will get, you will get 2 power n minus 1, and here you will get minus times n minus 1 minus 1. So here 1 and 1 will get cancelled, so you will left with this. And the fact that you have replaced n by n minus 1, then your like index of summation will goes from n is equal to 1, right? Because you have replaced n from n to n minus 1. So after doing that, again we can rewrite this. So here again if you see this expression, so here the power of z is n, but somehow you need to make it z power minus n, because this is what the definition of the z transform is. So how you can change the power of z to minus n? You simply replace n by minus n, right? So if you replace n by minus n, your limit will be minus infinity to 0, right? Because now you have replaced n by minus n. So if you replace n by minus n, this 3 power n will go into the denominator, because this will be 3 minus n, and then you can write it as 3 power n times z power minus n. Similarly on the right hand side you have n summation n from n is equal to 1 to infinity 2 power n minus 1 times z power minus n. Now it's very easy to see like what are the inverse z transform of this. So the sequence here will be for n less than 0, because the summation here is minus infinity to 0, so you have equality of n less than equal to 0. So this will be given by minus 3 times 3n minus 1, because 3 I can again multiply by 3 power n, and then the power of 3 will be n minus 1. So here you get minus 3n minus 1. Similarly, for n greater than equal to infinity, greater than equal to 1, I have this sequence. So for n less than equal to 0, I have minus 3n minus 1 sequence, and for n from 1 n 1 to infinity, I have minus 2 times 2 power n minus 1. Okay, so I hope this question is clear. The only important point was here to see this limit what is given to you. So if you clearly like able to identify like what common ratio should I choose so that my series converges, then it's very easy to solve such problems. Okay, so I hope this problem is clear, and we will move on to the next question now. So the next question is, you are given some sequence with two limits. So you have for n less than 0, you have sequence 6 power n, and for the n more greater than equal to 0, you have sequence 3 power n. And you need to calculate like what is the region of convergence of the following sequence of the Z transform. So first you need to calculate the Z transform of this, and then you need to calculate like what is the region of convergence, right? So again, it's a very easy problem. So let's go through the solution of this. So what you have first, you have you can write like Z transform Z of un from minus infinity to infinity un times Z power minus n. So this is what the definition of the Z transform. Now you see you are given sequence here in like two separate limits. So for n less than 0 you have 6 power n, and for n greater than equal to 0 you have 3 power n. So here what I am doing, I am breaking the summation here. So for n minus infinity to minus 1, I am rewriting this, and for n is equal to 0 to infinity, I am again like I am just separating this summation with two limits, right? So here if I see from n less than equal to 0, the value of un is 6 power n. So here the summation index of summation is from minus infinity to minus 1, so I can replace sequence un by 6 power n, right? And similarly on the right hand side, the index of summation is from n0 n is equal to 0 to infinity, so I can replace sequence un by 3 power n, right? Now what I can do, here you see the limit is from n from minus infinity to minus 1, but if I somehow replace like n with minus n, then this limit will be from n is equal to 1 to infinity, right? So if I do that, I will get 6 power minus n times Z power n, and from limit n is equal to 1 to infinity. Similarly, on the right hand side, I am again rewriting this expression. So I have n summation from n is equal to 0 to infinity 3n Z power minus n. Okay, so now this is, if you just now expand this, right? So for n is equal to 1, this will be Z by 6, and for n is equal to 2, this will be Z square by 36, and so on. So what I can do, I can just take the Z by 6 outside from this, right? And I can get 1. If you put n is equal to 1, you will get 3 by Z, and so on. So here it's both of these expression are like geometrical progression series infinite GP, and the summation and the series formula of that is very 1 minus Z by 6, because the common ratio here is Z by 6, right? And the common this, you need to make sure that the modulus of Z by 6 is less than 1, right? Then only this series converges. And similarly here I need to write the modulus of 3 by Z is less than 1. So if I take the union of both these limits, what I will get? I will get the modulus of Z should lie between 3 and 6, right? So this is what the question was asking. So the region of convergence of this Z transform will be modulus of Z will lie between 3 and 6 in order to make sure that this series converges. Okay. So I hope this question is again clear. So what I will do, I will move on to the next question now. Okay. So the next question is, if you have some sequence un, and the Z transform of that sequence is given by Z plus 2 upon Z square minus 4Z plus 3, right? Then what will be the limit of un when n approaches to infinity? Okay, so now if you recall, if you go to the first slide, then you see the formula here. If you someone is asking you like what is the limit of un approaches to infinity, then you can use this formula, which is the final value theorem, in order to solve such problem. So if we do that, right, so here the uz is given, and we will use the final value theorem in order to solve this problem. So if we do that, from the final value theorem, the limit of un n approaches to infinity can be written as limit z approaches to 1, z minus 1 times uz, right? So z minus 1 times uz is nothing but z plus 2 upon z square minus 4z plus 3, right? So it will be z minus 1 times z plus 2 upon z square minus 4z plus 3. Now if you take z is equal to 1 in this is basically a 0 by 0 form, right? If you just directly take z is equal to z approaches to 1. So what you do, you again can use the L'Hopital rule in this indeterminate form. So basically you take the derivative in numerator with respect to z, and similarly you take the derivative in denominator, and then when you try to satisfy this limit with z approaching to 1, you will get the value minus 3 by 2. So I hope this was a very easy problem. And so the answer of this question is, if z un is given by capital uz is given by this, then the limit n approaches to infinity sequence un is given by minus 3 by 2. Okay, so again I hope this problem was easy, and this like the I guess the very easiest problem in the whole assignment. So and I hope every one of you was able to do that. So now let's move on to the next problem, which is the seventh problem. So if you have again the capital uz is given to you, so the capital uz, which is the z transform of some sequence un, is given as z upon z minus 3 plus z upon z square minus 1, right, with modulus of z more than 3 here. Then the z transform of un plus 2. So again, if I ask you like what you need to use in order to solve this problem, then it will be again the initial value theorem, right? Because using initial value theorem you can write like what are the functions u1 u0 un, like that. Okay, so let's, if we do that, so we know if z of un plus 2, right, z of un plus 2 will be z square times uz minus u0 minus u1 by z, right? Now if we so this is the coming from the initial value theorem, right? So z of un plus 2 is z square times uz minus u0 minus u1 by z, right? Now first, in order to calculate this, what you need to do, you need to first find the value of u0. So the value of u0 is given by limit uz with z approaches to infinity. So if I take the limit with z approaching to infinity on the function uz, if I take the limit here on the this function, I will get 0 because the denominator has one more power of z. But here the as the numerator and denominator both have same power, if I use a L'Hopital rule, I will get the limit z approaches to infinity uz is equal to 1, right? Similarly, I can calculate like what is the value of u1. So the value of u1 is given by limit z approaches to infinity z times uz minus u0, right? So u0 here is 1, so I can rewrite again. So it will be limit z approaches to infinity z times z upon z minus 3 plus z upon z square minus 1, right? So again you need to take the limit here with z approaching to infinity. So what you do here, you try to solve the take the LCM of this, and then you try to take the limit of z approaching, you will get the value of u1 is equal to 4. So this is like a easy part, so I am not putting any time on that. So I hope this is very easy and you can calculate like what is the value of u1. So the value of u1 will be 4. So now you know both the value of u0 and u1, right? So the z un plus 2 can be written as z square times z upon z minus 3 plus z upon z square minus 1 minus 1 minus 4 by z, right? Because value of u1 is 4 and I can rewrite this. So again, here you can simply take the LCM in the denominator and then you can rewrite this equation. So if you take the LCM here, so one of the z will be cancelled by z square. So in the numerator you will left with just one z, and then you have 9z square plus z minus 12 in the numerator, and in the denominator you have z minus 3 times z square minus 1, right? So this is the answer of this problem. So again, here we use the initial value theorem and some property of Fourier Z transform in order to solve such problem. Okay, so again emphasizing, so this initial value theorem is again a very powerful tool in many of the application of whether it's physics or mathematics. So please keep in mind that all of these properties. Okay, so again let's move on to the next question then. So here you need to use the convolution theorem uh, to find the inverse z transform of the capital uz function. So the capital uz function is given by z square upon z minus 5 and z plus 3, right? And you need to calculate like what is the inverse z transform of this using convolution theorem. So let's see how to do that. So here the uz is given by z square upon z plus 3 times z minus 5, right? So what I can do, I can rewrite this expression by separating that z in the numerator. So I can write it as z upon z plus 3 times z upon z minus 5, right? So now you know from the convolution theorem, so if you have inverse z transform of this this complete function, then this can be written as the convolution theorem of these sequences, right? So if I take the Fourier inverse transform z transform of z upon z plus 3, then this can be easily calculated and it's given by minus 3 power n, right? And similarly I can calculate the inverse z transform of z upon z minus 5. So the inverse z transform of z upon z minus 5 is given by 5 power n, and these are actually very easy to calculate, and I am hoping that these things you already know. Okay, so now I am using the convolution theorem of the inverse z transform. So here what inverse z transform convolution theorem says, that if you have a some function uz, and then u times v uz times vz, then the inverse z transform of that is given by the convolution of their sequences. Okay, so the sequences here are minus 3 power n and 5 power n. So the convolution theorem can be written as summation for index m is equal to 0 to n times minus 3 power m, and then you have a 5 power n minus m. This is again coming from the convolution theorem of two sequences, right? So here what you can do, as this 5 power n is independent of m, you can take this outside, right? And I can rewrite it as summation m is equal to 0 to n minus 3 by 5 power m, right? And now what is it? It is again a geometrical progression series with the number of terms n plus 1, right? So here I am using the formula of the geometrical progression series with number of terms is equal to n plus 1, and I am rewriting the summation of that. So now if you simplify this, you will get to 1 by 8 times 5 power n minus minus 3 power n with n more than or greater than equal to 1. Okay, so again this question was just demanding to use the convolution theorem of the inverse Z transform, and actually this theorem is very powerful sometimes to calculate the inverse Z transform of any function. So please keep that in mind of this convolution theorem, and how this is powerful to find the inverse Z transform of some capital UZ functions. Okay, so this was the eighth problem. So now let's move on to the ninth problem. Okay, so ninth problem is using convolution theorem, you need to again calculate the inverse Z transform of the following function uz. Okay, so again if you compare this function, this question is similar to the previous question, right? Because the questions are same but the expression of uz are different in both of these cases. So what we can do, we can again do the same convolution theorem of that. So what I am doing here, I am separating it as z square upon z minus 2 whole square. Similarly, I am writing it as z upon z minus 3. So here I have just distributed the z power cube by giving z square here and one single z here. Okay. So here again I am using the convolution theorem. So the convolution theorem of inverse Z transform says it results into the convolution of two sequences. Okay. So here the only thing you need to know, like what are the inverse Z transform of these functions. Okay. So you already know the inverse Z transform of Z upon Z minus 3 is 3 power n. Similarly, you need to calculate like what is the inverse Z transform of Z square upon Z minus 2 whole square. So what you can do in order to find the Z transform of this, either you can use some Z transform properties to calculate that, or what you can do in a easy manner, you can again apply like separately the convolution theorem on just this function by writing it as Z upon Z minus 2 times Z upon Z minus 2. So you already know like what is the uh, 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 inverse Z transform of Z upon Z minus 2. So that is given by 2 power n, right? Similarly, now you can take the convolution of 2 power n with 2 power n and you will get the this inverse Z transform. Okay. So if I now try to calculate the inverse convolution of these two sequences, what I again using the convolution theorem, I can write it as summation m is equal to 0 to n m plus 1 2 power m times 3 power n minus m, right? And this 3 power n is independent on m, so I can keep it outside and I can write it as summation m is equal to 0 to n times m plus 1 2 power m times 3 power minus m, right? And I can again rewrite it as 2 by 3 power m by taking the power m common in these two expression. Okay. So now if you see what is this, this is nothing. If you just expand it, you can write it as 3 power n times 1 plus 2 times 2 by 3 plus 3 times 2 by 3 square plus 4 times 2 by 3 whole cube. Similarly, going up to n, it is n plus 1 times 2 by 3 power n. So this is what, this is nothing but a combined arithmetic and geometrical progression series, and it's very easy to write the general expression of this complete AP and GP series. So the formula of that I think you already know, like this we have studied in like class 10th. So if I so the common ratio of the geometrical progression is given by 2 by 3, and similarly the geometrical series arithmetic series is 1 plus 2 plus 3 plus 4. Okay. So you can just use the formula of the arithmetic and geometrical progression series and you can rewrite this. Okay. So here I am not spending much time on this because I think it's very easy to write the summation of this complete series. So the summation of this complete series can be written like this. So you have 3 power n times 1 minus 2 by 3 power n times 2 by 3 upon 1 by 9 minus n plus 1 2 by 3 power n times 2 by 3 upon 1 by 3. And now if you simplify this expression, you will get your answer for the following problem. So the answer of the inverse Z transform of this capital function uz is given by 3 power n plus 2 minus 2 power n plus 1 times n plus 4. Okay. So I hope this question was is again clear to you. So please keep in mind like all these following formula of calculating like what is the sum of some geometrical progression series of infinite GP, or it is with some number of terms like n, and similarly the summation of the arithmetic progression series, and similarly when you have this type of series which is a combination of both arithmetic and geometrical progression. Okay. So I hope this question is clear. The only point here was to use the convolution theorem and to calculate the inverse Z transform of Z square upon Z minus 2 whole square. Okay. And that I have already told you. You can separately use convolution theorem on just this function by separating it into two equal parts, and then you can easily calculate like what is the sequence corresponding to this function. and the sequence here will be n plus 1 times 2 power n. Okay, so let's move on to the last question for this problem set, and then it will be the end for this problem set. So again, you are given some function capital UZ, which is given by z square upon z plus 2 upon z square plus 4, right? And you need to calculate like what is the inverse z transform of this. Okay, so let's see how to solve this problem. So again, in class you have studied like how to calculate the inverse Z transform by writing uz in terms of partial fraction, right? So this thing we will use here in order to write that. This in terms of partial fraction by writing it as a upon z plus 2 plus b upon bx plus c upon z square plus 4, and from there you can calculate like what are the coefficient b and c covered and solve some problem in class. So this is a very straightforward. So the only thing is you first write it as, you first take this 1z in the denominator, then you rewrite it as in terms of partial fraction, and then you again multiply this function uz. So the uz here is minus 1 by 4 times z upon z plus 2 plus 1 by 4 times z square upon z square plus 4 plus 1 by 2 times z upon z square plus 4, right? So now what you do, you just take the inverse z transform on both left hand side and right hand side. So if you do that, so here you will write z inverse of uz, and similarly here you can use the linearity property by rewriting minus 1 by 4 inverse z transform of z upon z plus 2, and then you can write uh, this as uh, 1 by 4 you just take the inverse z transform here, right? So the inverse z transform here will be z inverse of z upon z plus 2 plus 1 by 4 z inverse of z square upon z square plus 4 plus 1 by, so the series here can be written as the sequence corresponding to this you can easily calculate. So this will be given by minus 2 power n. But now the problem is to calculate the, so now if you recall first problem, right? So if I go to first problem, okay, like sorry, second problem, you can see here if I replace square plus 1, right, if you replace theta by pi by 2 you will get z upon z square plus 1. Now if you compare it to the given expression, so what you have 2z square upon z square plus 4, right? But from when you put theta is equal to pi by 2, the z transform of sine n pi by 2 is z upon z square plus 4. But if you use the property of a power n times sine uh, n theta, then you can see if you put a is equal to z by 2, right? A is equal to a is equal to 2 in that. So if you put a is equal to 2 in that, then you need to replace z by 2, right? So using the standard function of like a power n sine n theta, the inverse z transform of this equation can be written as 1 by 4 times sine n pi by 2 times 2 power n, right? And similarly if you do the same business for the series like a power n times cos n theta, you will get this type of inverse z transform. Okay, so again just to emphasize on this, so these expression you see the z transform of sine n theta is really important because you need to guess like, oh, this looks like the like by doing some manipulation this looks like the inverse z transform of cos theta function, cosine theta function, and similarly by doing some manipulation on this, this looks like the inverse z transform of some sine n theta function. And here if you use the damping rule on that, you will get the inverse z transform of these following sequences. Okay, so the answer of this question is z inverse of uz is given by minus times minus 2 power n minus 2 plus 2 power n minus 2 times cos n pi by 2 plus sin n pi by 2. Okay, so here we see that first how to use the property of separating into the partial fraction when you need to calculate the inverse Z transform, and then how you can just guess like what are the inverse Z transform of these some typical functions like z square upon z square plus 4 and 2z upon z square plus 4 by just recalling the Z transform of the a power n sine and theta function. Okay, so this was all about the problem session 9, and I hope this video I will upload like after 2 days from the live session. And so whoever has uh, done this, then you can just go through the solution once, and then you can try to solve the problem. So okay, so this is all about this problem set. So I hope you get all the ideas. So I will meet you in the next problem session, which is the problem session 10, and we will be solving some of the problems from the problem set 10. Okay, thank you and have a nice day.